Hello, I'm Joshua Hyman, and the project that I made for the physics project is a catapult system. The main structure of this was actually made out of wood. Then the components that makes up the lever arm and the rotating axle in the center of it are made out of natural gas piping with a four-way at the center, allowing the axles to be connected to everything. There is a stopper right at the top of it, so that way once the ball is launched from here and goes all the way to the bottom, it will stop right here, launching the ball that is loaded out a certain distance. And I'm using the principles of E equals E2 in this equation because it goes from potential energy at its max height and then converts it into angular motion as it's falling down, because this is a rotational energy. Once it stops, though, then the ball almost instantaneously goes from a rotational energy into a linear velocity, and then it launches it at the speed of the angular velocity converted into linear velocity. But then gravity starts taking over again, pulling it back down to Earth and causing it to land a certain distance away. Then in my second experiment, I actually doubled the length of the bar. So instead of here, it went out to here. That actually increased the height from here all the way up to here, causing it more potential energy because we went from mgh to mgh times 2. Since we doubled the length of the bar, we increased the height the bar could go. This increased the speed of the rotational energy because it's going from mgh to angular velocity. Then it went from angular velocity to linear velocity. And since energy can be lost through friction and other forms, but the total energy output is almost doubled due to us doubling the length of it, it will actually cause it to go roughly double the length of it. As you can see in my experiment, it doubled the length of it, causing the ball to be launched at double the speed, causing it to go double the distance since the energy is doubled overall. It also, though, caused the ball to launch higher. And that is the physics behind a traditional catapult. Now, there are other catapults with a sling system where it has the same counterweight system, but has a mechanical sling like so, as demonstrated when it reaches its apex. That causes the thing to swing out, releasing it at a higher height and with a higher velocity because it's going from a slower armed rotational hand to a smaller one with a higher rotational energy system, meaning higher linear speed. And this overall is my system of trying to launch a tennis ball across my yard. Was it successful? Kind of. I just need more weights, but in my first experiment, we actually ran into the trouble of the piping itself broke. Right here at the connection point where everything was connected, at the threads, there was enough energy in the system from it falling at this height, at the original height and length of the first bar, to snap it, causing it to break. Now, this is steel, about an eighth of an inch thick, and it snapped the energy. That's a lot of energy for a piece of brick attached to some piping. And this goes to show that's a lot of energy being transferred into a rotational, then to a linear. And we got about about 5 feet from the catapult on the first try, and the second time we got about 9 feet. This is probably due due to the system having a lot more friction in the system because of the higher energy system due to coefficient of friction in the bar system itself. Well, thank you for listening. Hope you have a wonderful day.